Hello? Okay, so let's continue with the last talk of the day with Arman. Thank you so much, Arman.
Thank
for
you.
coming.
Thank you, Fernando, for the invitation. It's my third time in Natal, but it's every time enjoyable. I'm going to talk about the IceCube neutrinos and the possible interpretation in terms of the heavy dark matter. I'm going to talk more on the phenomenology than the theory, convincing you that the heavy dark matter can exist. You had already a talk on the freezing. In principle, the freezing mechanism can work for the heavy dark matter. But before going to the theory side, which I have some slides in the backup, if you wanted, we can discuss. But let's see if there is any reason to think about the heavy dark matter and how it's possible to probe them. The slides that I'm showing, the result that I'm showing is based on these 5 papers, most of them with Pasquale, but there are other people like Sinkyukan, Sergio Palomares Ruiz, Inas Arcevic, and Atri Patachir. So, because I assume that not everybody is from the neutrino background, so I just very briefly discuss the IceCube observation, what IceCube have seen, and what is IceCube. So here you can see the neutrino sky, energy in the log scale, and the flux on the y-axis, again in the log scale. So we have several components there. Some of the components, like the relic neutrinos, there is no even hope for the near future detection of them. But several other components have been already seen, like the solar one, supernova, at least one of them, 1987, we have seen. We are looking for the relic and, in principle, some near future ones that are happening again. We have the atmospheric neutrinos with this flux, and there are expectation for some other sources of the neutrinos from astrophysical processes like the GRB, like the active galactic nuclei, and also from the GZK mechanism, what we call the cosmogenic neutrinos. These are the ones that we are also expecting to have them in the very high energy, but also, as you can see, in the very low flux. So, as you can see, the flux is, but the astrophysical one also in principle go to the lower energy, but the problem is this huge background that we have here for the atmospheric neutrinos, which means that if you want to observe this one also, you have to go to high energy, at least to get rid of these atmospheric neutrinos. And when you go to high energy, the flux drops very fast, and that means that you need a huge fiducial volume to be able to see them. And that was the main idea behind the neutrino telescopes, to build very huge telescopes that the fiducial volume is so large that the number of events that we get from such a small flux will be observable. So this was the idea behind the IceCube. I'm going to talk in the next week, in Monday I have another talk, which I'm going to talk just about this part in the IceCube, but for this talk I'm going to focus in the astrophysical part. But this is atmospheric neutrinos, which is basically background for the astrophysical neutrinos. Actually, they are very useful, and we can probe a lot of new physics with them, which is going to the neutrino part. So this is the IceCube in the South Pole. Is a kilometer cube experiment. Is 86 strings of the photomultipliers implemented inside the ice from the depth of 1.5 to 2.5 kilometer. There is a part inside the IceCube, which is the strings are more concentrated, so the distance between the PMTs are smaller, which means that the energy, the threshold of the detection is lower, and which is called the deep core. And the Amanda was like the first prototype of the experiment, is a proof of principle that it can be, and then after that expanded to the whole IceCube. The energy threshold of the observation in the IceCube is more or less 100 GeV. For the deep core is more or less 10 GeV. And if you put more concentrated ones, you go even to lower one, which is 1 GeV, and you can do oscillation physics. That was the idea behind the Pingu part of the IceCube, which is not going to happen as far as I know. I'm not from the IceCube collaboration, so I'm just, I know whatever I heard in the conference. So the detection principle in the IceCube is more or less like the other Cherenkov detectors for the neutrinos. So the neutrino comes, or either inside the volume of the IceCube or outside of the volume of the IceCube, close to the vicinity of the implemented volume. It have a interaction. It can be a charge current interaction or neutral current interaction of any flavor of the neutrinos. I will discuss later. It produces a muon, for example, and the muon in the high energy, they have a more or less 3 or 4 kilometer range, so they can propagate inside the ice, and the velocity is higher than the velocity of the light inside the ice. They produce the Cherenkov radiation, and the Cherenkov radiation can be detected by the PMTs. So this is the basic idea of the detection of the neutrinos in the IceCube. Of course, it's a bit more complicated. You can generally have two kinds of events, which we call them the muon track events and the cascade events. The muon track events comes from mainly from the charge current interaction of the nu mu bar, which produce a muon, and then the mu propagates inside the ice. This is a real event of the IceCube. This is not a simulation, but it's a real event. You can see the direction of the propagation of the muon inside the volume of the detector. The color is the timing. So it exactly shows you from which direction is coming, and you see the path. The other type of the events that you can see is the cascade events, which are basically a spherical ball of the light, which is coming from the hadronic showers. And it can come from the neutral current of any neutrino. It kicks the nuclei, and the nuclei will produce a shower. Or it comes from the nu E-CC interaction, which produce electron or positron, and then you have electromagnetic shower. Or it can come from the CC interaction of the nu tau, and then the subsequent hadronic decay of the tau, which gives you another shower. So this is again a real event. You can see the cascade, which is like a sphere. Obviously, by eye, you can see also each of them has a good or bad aspects. The good aspects of the muon tracks is that you have a very good angular resolution, because you are seeing a track. But the energy resolution is poor, because you don't know where was the vertex that the neutrino that the muon has been produced. So the muon will lose some of the energy outside of the detector before coming to the detector. On the other hand, for the cascade, you don't have a good resolution, because it's like a sphere. Is more or less 10 to 20 degrees. But the energy resolution is much better, because it's like a calorimeter. All the energy is deposited to the detector. So the IceCube started with this. It's much more complicated than this, but IceCube started to look for the neutrinos, and they have seen 2 PeV cascade events in 2000, if I remember, 13, yeah? Which, when you have 2 events, you can call them by name, is Bert and Ernie. Both of them are 1 PeV energy. And the question is that what is the source of these 2 neutrinos? So in principle, you can do a fit to 2 events, which means that you can just check the normalization of the flux, not the index. And that orange line will give you such a fit, which is with this normalization of the order of 3 10 to minus 8 GeV per stradian per centimeter cube per second. The question is that if they can be cosmogenic, is very low probability to be cosmogenic, because the expectation for the cosmogenic at this range of the energy is much lower than this. You can say that I don't know very well many things, maybe the normalization is higher, but then if you push this up to these 2 events, then you have a lot of more events in the high energy, and IceCube is very sensitive in the high energy. So it's not this that the IceCube is losing its sensitivity in the high energy. No, IceCube should have seen much more events here. So is this really a kind of cutoff that, at least for these 2 events? So the question is that where are the rest of the events? IceCube started to look for the high energy no events at that time, but they started to think about a very clever way of rejecting the backgrounds, which at the end led to something that they call it the Hesse analysis, high energy starting events, which they use a layer of the detector as a veto, and then they can reject the background, which is the atmospheric muon and atmospheric neutrinos in this analysis. By rejecting these backgrounds, they found a set of other events in 2 years, which all of them, in principle, can be astrophysical neutrinos. There are some backgrounds inside. Totally 28 events at that time. So the x of the events, including the background, if you do the analysis, is more or less 5 sigma, 4.3 sigma, which is like evidence, a strong evidence for the astrophysical neutrinos. And the source are not identified still. No cross correlation with the known astrophysical objects gives you any positive results for the possible sources of these neutrinos. And this will continue until the last data that I will show you later. There is no sources still identified. So here we can see the events in terms of the deposited energy inside the detector is equivalent to the energy of the incoming neutrino with some factor, depending on the shower or track, and the declination. And you can see that is more or less isotropic. Remember that in the high declination, you expect less even because the Earth is opaque to the high energy neutrino, so they cannot pass the neutrino, the Earth to come to the detector. So taking these events, at that time with Pasquale, we started to think that if it is possible to interpret these events in terms of the decaying dark matter with the very heavy mass of the order of PeV. I'm going to talk about these aspects, but before that, let me mention that we don't know really what is the mass of the dark matter. WIMP is a very beautiful scenario, but it's not guaranteed. And if we think more, more freely, we can see that the mass of the dark matter can be anything from the axion to the Gauss scale, or even higher. And we should be careful about this light effect, that if you lose your key, it don't mean that it's just on the place that the light is there. So we have to look at the place, at all the possible places, when there is a light or when it is possible to look. And this effect comes back to this guy, which is Mullah Nasreddin. I don't know if you know him. He's a funny character with a sense of humor in the literature of the Middle East, which doing funny things. One of the things that he was doing was this. It's fictitious, but he was losing his key and was looking at some place. Somebody asked him, "Why you are looking here? What you lost?" He said, "I lost the key of the house." And where you lost? I lost it 2 streets away. So why you are looking here? Because there is no light there. Light is here. And we have to be careful about this effect. And basically, we had already a light. We were looking a lot there. Still we are looking at. We have to look. But there are some other street lights. We have to keep into mind that it's possible to look at the other places. And IceCube is one of these possibilities. And the question basically that I'm going to answer today is that if there is a heavy dark matter PeV scale, what will be the signatures? And how we can probe this dark matter. So let's go to the IceCube events. So if you have a high energy dark matter, high mass dark matter, heavy dark matter, basically you have two diagnostics, which are the energy distribution and angular distribution of the expected event from the decay of the heavy dark matter. Let's start with the energy distribution. So there are two contributions into the events that are coming from the decaying dark matter: galactic contribution and the extragalactic contribution. The galactic can be calculated by this line, integral over the line of sight, with the first power of the density. Because it's decay, we are using NFW but because we are analyzing the decaying scenario, you are not very sensitive to which profile you're using. Because most of the contribution is coming from the halo, not from the galactic center. And then we have the extragalactic contribution, which basically you have to take into account the redshift of the energy. And the one thing that is here, which is dN over dE, which is the neutrino production at the point of production, and that is the particle physics part, and that depends of the model of the dark matter that you have and how it couples to the standard model. generally, you can assume that there are two different types of the channels, which we call them the soft channel and hard channel, with a branching ratio, which is giving the branching ratio to the hard channel. Hard channel, I mean the channels that are producing more neutrinos close to the half of the mass of the dark matter is a decaying dark matter. And the soft channel, which are the channels which are producing more events in the low energy with respect to the mass of the dark matter, which are coming from the hadronization of the products of the decay, which means that generally these channels are the quark channels, and the hard channels are the dark matter going to neutrino or to charged leptons. And of course, you have to take into account the oscillation, but that is the easy part because it's a decoherent oscillation of the neutrinos from the point when they arrive to the Earth. So let's look at some examples of this. For example, if you have a 4 PeV mass for the dark matter and you have a lifetime of the order of 10 to 27 seconds, I'm showing here different channels, basically all the possible channels for the astronomy of the particles. Here you have the hard channels. You can see that there is a peak, more or less, in the half of the mass of the dark matter. And then you have lower energy events, and that comes from the electroweak corrections. Electroweak corrections is completely responsible, for example, for this part of the curve, because if there is no electroweak correction, there will be no neutrino produced from the dark matter going to electron-positron in the lower energy. So all of these are coming from the electroweak corrections. And then you have the soft channels, which are these quark ones, which giving you more neutrino in the low energy, higher flux in the low energy, and some intermediate channels, which are gauge boson, which are enjoying both the electroweak corrections and the hadronization, depending on the decay of them. So that gives you this, for example, W and Z, which gives you more or less flat spectrum in the range. So if you sum the two, for example, let's assume you have a dark matter with the mass of the 2 times 1.6 PeV, with the branching ratio more or less 10% going to the hard channel. And hard channel, I'm taking here nu E, and the soft channel, I'm taking any light quark. And then you have this, here I'm showing the blue line is the galactic contribution, the red line is the extragalactic contribution, is red shifted the peak, so there is no peak anymore. And then the sum of them is shown in the black, which has some features. That is the main point, that you have some features in the flux. It's not featureless flux with respect to the energy. Of course, there are some characteristics of this kind of flux. There is natural cutoff in terms of the dark matter scenario, which is half of the mass of the dark matter. And then you have the population in the low energy, which comes from the electroweak interaction and the hadronization. And depending on the channel, most of the time you can produce like these kind of features in the energy. You may think that these are very special. I'm fine-tuning here, assuming one special kind of the channel nu E and then the Q and then 12%. But it's really is not this. You can see here several different benchmarks gives you more or less the same kind of flux for the neutrinos. Then we have done this fit for the 2 years data at that time in the IceCube 2013, and you can see the red line is showing the dark matter fit, and the blue line is showing the E-2 spectrum astrophysical isotropic distribution. But of course, IceCube is taking more data. I already included several slides of the 2 years and then 4 years and then 6 years, but I'm not going to show all of this to you and discuss to you. I'm going to skip several slides and showing the last ones, which are more appropriate to show. But after that, IceCube continued to take data. This is the 3 years data set with 37 events. And you can see here the angular distribution of the data in the galactic coordinate and the energy distribution of the events are here. You can see more or less there are 2 bins that there were no events there. Still one of them there is no event there, but statistically it's fine. It's not a big deal. And here you can see the expectation of the flat E-2 or it should be E-2, yeah. The E-2 spectrum is this dashed line. And this this bump that you can see here is from the glacial resonance. Yeah? We expect more events in the 6.3 PeV, which has not been observed any up to now, at least to be sure that it's glacial. The angular distribution is also showing some kind of enhancement with respect to the galactic center, but careful, because these are all cascades events with 15 degree in the resolution of the angular resolution. And in the astronomy, when you talk more than probably half a degree, is a joke to do any angular analysis. But there are muon track events like this, but these events that are here, they have huge uncertainty. So for the 3 years, we have done this base. Still, you can fit with the dark matter, just dark matter. That is the other point that I want to mention, because later I'm going to talk for the case that both the astro and dark matter exist. And at that time, we used this model which is very, very, tries to solve all the problems in the physics in one model, trying to solve the leptogenesis, the inflation, all the things, and also produce such a dark matter which is decaying, and this dark matter can produce such a neutrino. I want to emphasize that here we are not actually doing a fit. Here we are calculating the prediction of the model. So it's not a fit to the data. So let's come back to the question of the angular resolution. So we have the angular resolution. We have the angular distribution of the events, which is given here. For example, for the 3 years data set, you can repeat it for the other years. And then the question is that how we can see if the data are preferring some isotropic distribution, or what is the prediction of the dark matter for the angular distribution. Dark matter is predicting that the extragalactic part is isotropic. The galactic part is not isotropic, but is a decaying dark matter, so there is a mild enhancement with respect to the galactic center, and you should put it in top of the extragalactic one, which is completely isotropic. And take into account that the ratio between these two fluxes is fixed. It's not something that you play with them to reduce or to increase or decrease the part of the galactic or extragalactic. This is fixed by the dark matter density. And then you have the extragalactic, you have the isotropic distribution, 1/4 pi, PDF of the probability distribution function, which is for the astrophysical generally sources, which they should be as isotropic. So you can play the game, you can start some statistical game, you have the PDF of the data, you can calculate the PDF of the isotropic distribution, the PDF of the dark matter, and you can apply several different statistical tests to see if the data are preferring this one or that one, and what is the confidence level. At which confidence level you can distinguish in principle the two PDFs using the statistical tests. I'm not going to the details. You can do the likelihood analysis. You can do some Kolmogorov-Smirnov test using the CDF of the PDF, or you can do some Anderson-Darling test, which is the most sensitive one. And at the end, you will get something like 2 sigma preference to the dark matter, but that don't mean, again, anything. Why? Because the data is small. The number of data is very, very small. And in some sense, it can mean that it means a very important thing, because the question is that if you have 50 number of events randomly distributed over the sky, what is the maximum confidence level that you can get from angular analysis? And that you can calculate, and it is at the order of 2 sigma. And the analysis is already showing you 2 sigma. So it can be a sign of something. But again, we need more data, obviously, to say something meaningful statistically. IceCube is continuing to take data, obviously. 4 years here, you can see the 4 years data set. From now, I'm going to show you the gamma here, which is the index, the best fit index of the IceCube. Here is 2.6, more or less, to the 4 years data set. And this is the angular distribution, is the equatorial coordinate, and the energy distribution. And now we have started to do some more general analysis, taking the dark matter and astro at the same time and trying to fit. And one of the reasons behind is that we want to see if this gamma can change if you include the dark matter. And that has a reason in the neutrino community, because in the IceCube, there are two different sets of data. One of them is the Hesse data that I showed you, which is here is 2.6, as I said, for the 4 years data. And then there is a true going muon data set, which the best fit of the gamma for that set is 2.1. And there is a tension between, because basically they should come from the same source. And then you have two different index, best fit value, for the data sets that are in principle the same thing. So the question is that if adding the data, the dark matter can resolve such a tension also or not. So this is the part that I'm just going to show you the figures. So here you can see, for example, a fit to the dark matter, to the IceCube data. The black line is from the dark matter, and the green line is from the astrophysical neutrinos. And you can see that, for example, with the astrophysical neutrino, with the index of 2.3, and assuming dark matter going to BB bar with a mass of 1 PeV, it can give you such a fit to the data. So dark matter is more or less interpreting the low energy part, and the astrophysical one, the high energy part. But this is for the soft channel. Obviously, if you go to medium, you see that the dark matter starts to contribute to the high energy and astrophysics to the low energy. And then for the harder and harder channels, for example, the neutrino, basically you can interpret the high energy and forget about the low energy. Just the astrophysical neutrino are responsible. So let's skip this part. Because I'm going to show you the 6 years data set. So I started to get more data. This is the 6 years data set. And now the best fit is 2.9. The tension is larger. Still that one is 2.1, the true going muon events. So the tension is getting larger. Maybe it is a sign that there are multi-component fluxes. It's not the same flux that they are measuring in both. And here is the angular distribution and the energy distribution. That is the one beam that I told you that still there is no event there, but statistically. And here you can see again the fit to the dark matter with the hard channel, for example, assuming the dark matter and astro together, and the one that is, I will call it the intermediate, not soft, not hard, dark matter going to W. And again, the scenario that is just dark matter works very well, even better than the astrophysical for the 6 years and 8 years data set. If you want, you can interpret the whole data by the dark matter. It depends on your taste, if you like or no, but it's possible. So the question is that, fine, imagine that we can do it, then the question is that how we can check such a scenario. What are the other signatures of a PeV scale dark matter? The other scenarios, obviously, there is no hope to see any charged particles from the PeV scale dark matter, but there is another channel which is the gamma ray, and that is very helpful actually. So let's look at the gamma. So we have the gamma ray bounds, but where these gamma ray bounds are coming? Basically, there are two contributions again to the gamma ray. Let's call it the galactic and extragalactic. And let's start with the extragalactic. But we know that our universe is completely opaque above the 1 TeV to the gamma rays. So there is no gamma ray with energy higher than 1 TeV that can propagate to our galaxy from the far distances, extragalactic sources. But what will happen is that they will be pair produced on the CMB or in the EBL, generally extragalactic background light, and they produce electron positron, they will be absorbed. But this absorption is not complete. What will happen is that when they produce electron positron, the electron positron will do an inverse Compton scattering again on the CMB and shoot the CMB gamma to the high energy. And then again you have another high energy gamma which do a pair production with the gamma, and this cascade process will continue. Is an avalanche that go to the low energy, and at the end this will produce a flux of gamma in the energy range of the 100 to 1 TeV. This has been observed. This will be a diffuse flux over this range of the energy that in principle is observable. On the other hand, the Fermi-Lat experiment, they have seen a diffuse flux at exactly the same range of the energy, this is the last publication of them. which they extend the energy observation of the what they call the IGRB. The IGRB is the extragalactic background light that they measure, subtracted the point sources from them. So this is the residual of the diffuse flux that remains, and it goes up to 800 GeV more or less. So whatever high energy process in the universe that you have will have such a cascade that I told you if they produce a high energy gamma, and they will contribute to this flux. So one thing that you should always be careful is that your flux should not overshoot this observation, otherwise you will have problem. This is a bit more tricky because you can say that already we have some models that what is the contribution to this, what is the source of this diffuse one, which are low energy faint blazars. And in principle, you have to calculate them also and then subtract, and the residual of that one should be used, but it's very tricky, that one. Maybe later I can comment on this. But if you take the whole IGRB, you can calculate the expected diffuse gamma ray from the high energy, from the dark matter. In our scenario, you can calculate it exactly, but just on the energetic, you can call that generally the energy, integrated energy, inside the IGRB is this value, 10 to minus 7 electron volt divided by centimeter cube. Total electromagnetic energy budget of the dark matter PV range is more or less 1 order of magnitude below that. And remember that the cascade process is a continuous process, so there is no peak inside the produced flux. So it will be below this. But of course, people calculated in detail in this paper of the Murals and the collaborators. They calculated the expected, this red line is the expected gamma ray from the dark matter in the PV range that can interpret the IceCube data, and this is the Fermi data, and you can see that it is compatible with the data. Talking about the diffuse flux, just let me mention something that recently there was a paper by the Michael Katcher-Rice and the collaborators, and they were claiming that they can do the analysis of the data of the Fermi outside of the collaboration, and they claim that actually if you extend the diffuse flux analysis of the Fermi to higher energy, more than 800 GeV, which was the last publication of the Fermi, the flux start to grow. And these 3 beans that you can see here are the result of this paper that they claim. I'm not saying it's correct or wrong. It's very tricky, this analysis. At the end, the Fermi-Lat correlation should confirm or reject this interpretation. But it's one of these kind of papers, or either is wrong or is very important. So let's see what happened. But taking this observation, this can be also a very nice hint to the heavy dark matter. Because again, you cannot have extragalactic TV diffuse gamma ray. It's impossible. So this should come from the galaxy, our galaxy. And our galaxy, how can produce such a high energy diffuse gamma ray? Either it should be a pivotron, which we don't have, or it should be a dark matter decay, or it's possible to change you should assume that the cosmic ray is propagating to higher latitude than what you were assuming before. So let's come back to the gamma ray bound. We have still the galactic contribution. So from the galactic point of view, you have to take into account also the absorption, as Pasquale today was mentioning. When you go to high energy, the gamma ray is more complicated. You have to take into account the absorption even at the galactic scales. Here I'm showing, for example, the opacity of the sky to the gamma ray for the gamma ray of the energy, for example, of PeV, 2 PeV. And you can see that even from the galactic center, which is the black line, is 70% absorption. So the gamma ray, with a high probability, will be absorbed even at the galactic scales. So this should be taken into account. And of course, the inverse Compton scattering also should be taken into account. Because the dark matter will produce electron positrons, and these electron positrons can shoot again the CMB or starlight of the galaxy to high energy and produce high energy gamma ray. So this should be calculated. It's complicated, the calculation. Let us skip the one, and this is the result. And you can show, I'm showing here the expectation of the dark matter that is interpreting the IceCube data. Here, the red line is the expectation from the galactic center prompt, and the dashed one is from the inverse Compton scattering, and from the galactic anti-center, and from the galactic pole, the blue and the orange one. And these are the data that we have in this range, which are coming from these two experiments, Casamiya and Cascade, which are kind of old experiments. I think they don't exist anymore. It's just the data is there. And you may say that, well, it seems that some of these have tension because this red line is above the green one, but actually you should take into account the field of view of these experiments. The Casamiya and Cascade, they are looking at this point of the sky, and this is the flux that you were comparing from the galactic center in the dark matter model. But you should take into account the Cascade and Casamiya, they are looking actually at the tail of the gamma ray, galactic gamma ray from the dark matter decay. So the Hawk experiment in principle can look for this kind of the galactic gamma ray. They already published, I don't know which year, I even didn't put the paper of them, but it's from Hawk collaboration. I think it was 2 years ago, that they published these limits on the dark matter, in the heavy dark matter from the galactic gamma ray, and these star lines are the best fit of the IceCube data in terms of the dark matter. But in their model, I'm not exactly sure what they do for the IceCube part. But you see that more or less they are touching the parameter space that you expect. Depends, of course, on the channel. If you go to the neutrino channel, of course, the gamma production is very, very small, and then the limit is completely. You had some paper on this, actually. Now I remember. So in future, the Lhasa and IceTop, which is the top part of the IceCube itself, can look for such a flux and gamma ray from the galactic, from our galaxy, and the other experiments, which is mainly the IceTop and the Lhasa, can probe such a parameter space that you expect for the interpretation of the dark matter, interpretation of the IceCube data by the dark matter. The last slide is this one, which we were thinking about, that in principle even it's possible to look at the anisotropy of the cosmic ray due to the gamma ray from the dark matter in the high energy, even without discriminating between the gamma ray and cosmic ray. So here I'm showing some dipole anisotropy that you can calculate due to the gamma ray divided by the total cosmic ray flux. This will produce some anisotropy, and this already, if you use the anisotropy, the measurement of the anisotropy of the cosmic ray, you can put a limit of 2.5 10 to 27 seconds on the dark matter, on the lifetime of the dark matter. And this is a factor of 4 or 5 less than the value that you need for the IceCube data. And in principle, in this line also is possible in the near future to probe these kind of scenarios. And here's the conclusion. I already told all of this. Maybe that's a better conclusion. So maybe there are something in the PV range. Especially we should take into account we are probing a new range of the energy. Let's be open-minded. Maybe there is something there. Thanks.
Questions?
Actually, I have a comment about this IceCube excess in the high energy. I remember I saw